Thanks. I'm Samir. I'm an engineer on the Dart Compiler and the Runtime, which we collectively call the VM. So I want to talk about the Dart type system and how the new Dart type system in Dart 2 has influenced our compiler. And I also want to clear up some misconceptions about the Dart type system and what types are good for and what problems they can also introduce. But before I start, I need to say that everything in the presentation is from my own experience and my own opinions, and none of this represents Google's opinions. And also, I'm not here to take credit for anything. Everything I talk about is the work of the entire Dart VM team. So why should you care about the Dart and the Dart compiler? Well, every Flutter app is mostly Dart. Not only the app code itself, but also the framework code is all in Dart. And this means that it's important for the Dart compiler to generate small code and fast code in order to have small apps and very smooth and responsive apps. So in order to understand the impact of types on Dart, we need to begin with Dart 1. This was the first version of Dart, and this is how the compiler was originally designed. So Dart 1 had a concept of optional typing. This means that you can add types to your program, but by default, they have no semantics. They're just comments. If you choose to run your program in checked mode, it turns on the types, but the types have no static meaning. They're not influenced in how the program is compiled. They're just assertions that get triggered at runtime. If you run the code like in a production mode, in the way that you deploy the code, you will normally choose to not enable your asserts and not enable the types. So there they have no impact. And in addition, they don't apply to any code that's not run because they're just like assertions. So if you have some code that doesn't get run in your tests, then your type annotations there have no influence either. In addition, Dart 1 introduced a few concepts that we still have in Dart 2, such as the reified generics and covariant generics. And the treatment of generics in Dart is one of the most challenging aspects that we'll see how to handle in the type system. So as an example of what optional typing means, here's a program where we define a wrapper for plus, which adds two numbers. If we pass in integers 1 and 2, then it does what we expect. But if we pass in a string instead, then we get an error. However, in normal Dart 1, this error doesn't come up until inside of the add function when we try to add the string in the int. And then we get an exception, which is thrown by string-base.plus. But if we run it in checked mode, then the num annotation for the type to add is enforced. And it's checked as soon as we call add. So then we get an exception much earlier. In addition, Dart has reified generics. So this means that when we create an instance of a generic class, we remember what the type arguments are. So if we create a list of int, and then we pass that object around, we can later find out that it's not just a list, but specifically a list of int. This is in contrast to other languages like Java, which have type erasure, and the generic types are eliminated. So you create a list of int, and later on, all you remember is that it's a list. In Dart, this interacts with the type system. So one kind of typing rule that's not allowed is you can't turn a list of int into a list of num. So if you try to run this program, which creates a list of int out of a list of num and then prints the first element, it'll still print you a double in unchecked mode. But when you turn into checked mode, then it throws you an error when you try to perform the cast. However, there's a similar unsafe operation, which is still allowed in Dart 1, and this is what covariant generics refer to. So in this case, instead of casting from a list of num to a list of int, we go the other way, and we cast from a list of int into a list of num. This cast is allowed. However, there's a problem, which is that if we then mutate the list as a list of num, for example, add some doubles and try to read them back out as ints, then we get an exception. So in order to prevent this, we then create an exception in checked mode whenever you call the add method. And so this error happens later than the case from a list of num into a list of int. And this is what it means to have the covariant generics. And we'll see that this turns out to be a problem in Dart 2. So this is what the type system of Dart 1 looks like. How do you compile a program where the types are meaningless or the types can't be trusted? Well, the answer is Jit Compilation. So Jit Compilation is a technique of compilation which involves three principles. The first one is that we don't compile any code until it's used. So functions in the program which never get called when you run the program, they never get compiled. In addition, once we compile them, we only compile them in the fastest way possible and into unoptimized code. We only optimize them once we decide that they're hot because they've been run many times or some performance counter is triggered. And then the final principle is speculative optimization. So by profiling the code, we can then optimize it better. So we can see that, for example, some functions are hot, and we can choose to inline them more aggressively than other functions. Or we can see that the types of some variables are always a certain thing. For example, in the first case, we might see that in add, the types are always ints. And then we can optimize the plus function on that basis. So in our Jit compiler, we start with the Dart source code. This is an example actually from Flare, where it's animating the skeletons inside of a thing. In any case, it's some hot code in Flare. So we start with the source code, and then as soon as a function is compiled or is executed the first time, then we generate our intermediate language. This is a control flow graph with stack-based instructions. So each of these instructions, like store local, load local, or push argument, are manipulating a stack. And then at the bottom, we have some instance call, which represents calling some method. Once we've created this, in the unoptimized mode, we generate assembly immediately before performing any optimizations. And then we can start running the program. However, this is not very efficient assembly. So if the code is run many times, we then optimize it. So we go back to the IL we created at the beginning, and we convert it to SSA form and apply a number of optimizations on top of that, like register allocation. And then finally, from that, we generate optimized assembly. The optimized assembly runs much faster than the unoptimized assembly, but it also takes us longer to generate because we have to run all the compiler optimizations. So for this reason, we only run it on code once we know that it's hot, rather than eagerly running it on any function that we might need. So the JIT, in addition to having a tiered architecture, the JIT also has a cyclic architecture. Because we can perform these speculative optimizations, we might say that, for example, we believe this variable is always going to be an int, but we can't prove it. So we'll put an instruction like check smi or check class, which will say, check that our assumption is true, and then execute the code that was optimized on those grounds. But these checks can fail. So when they fail, we have to de-optimize the code, which means we throw away the optimized code, and we go back to the unoptimized code, which doesn't make these assumptions. But once we go back to the unoptimized code, maybe the code is still hot. So we re-optimize it later on with new profiling information. So because of this, the JIT is a cyclical system. We start with the source code, we generate unoptimized code, we optimize it when it's hot, then when our assumptions fail, we de-optimize it back to unoptimized code, and so forth. And there are other situations that can cause us to de-optimize, such as hot reload in the case of Flutter. So in order to kind of illustrate how these principles actually work, we're going to take a look at this simple benchmark. So this function, sum squares, it just creates the cumulative sum of all the squares from one list and puts them into another. So it's a very simple mathematical algorithm, and we should expect it to be pretty fast. We should expect a loop which does some loads, some stores, and some arithmetic, and not much else. But in order to get there, we have to go through a lot of calls first. So according to the Dart language, there's the plus and the times. They don't mean necessarily multiply and add. They just mean call the method star against this function, against this variable. Call the method plus against this variable. So in order to compile that, we have to start by interpreting it as the Dart language says, which means that we have an instance call against the list, which is for each. Then within each loop, we have to call instance call against the length of the list to check the length. We have to call instance call against the less than function in order to compare the loop expression. We have to do more instance calls to implement the star and the plus and the add. Because without the types, we don't know that we're adding numbers or multiplying numbers. We could be calling any random function on any random object. So in the unoptimized code, we can't make any assumptions, and all of these operations are instance calls. But this is very slow. So as the code warms up and we gather profiling information, we can tell, for instance, that the instance call on the bottom left is referring specifically to a fixed length list. And we can inline the implementation of for each. And then we can also inline the implementation of integer arithmetic for the star and plus, because we can see that only integers actually flow into those call sites. So once we've done all of this, then we end up with the optimized code for sum squares. And in this case, you can see some of the speculative checks at the top. So we have a two-check class. These correspond to the input and to the list and output parameters. And we check that the first one is a fixed length list and the second one is a growable list. And then on the inside, we do check smi, which verifies that the value we read from the list is in fact an int. Once all those checks have performed, we can then do actual arithmetic with the star and the times and plus and comparison operations. And so there's no more instance calls left in the hot path of this loop. We can also look at the assembly, where we can see that these speculative checks for the class and the SMI are only a few instructions in a branch, which is much faster than doing an instance call if we didn't know or couldn't do anything based on the type. So this is all great, and this is a great way to compile Dart 1. And this is also similar to how JavaScript, which has no type system, is compiled. But it has a lot of challenges, specifically when we want to compile code in an ahead-of-time way. So then we have Dart 2. So in Dart 2, there's no longer optional typing. Everything is typed. If you choose to not write a type, then type inference will figure one out, and if it doesn't figure one out, it'll put in dynamic. And as a consequence, the type system is sound. So now the runtime checks that we had from checked mode, they are not as prevalent, but where they do still exist, they have to be run. There is no way to opt into them or opt out of them. They are simply there. And as a consequence, we have a sound type system, which means that the compiler can actually begin to use these types to optimize the program. So if we go back to some of our examples, we can see how these programs behave in the Dart 2. So in the first case, this program, which was previously gave us an error on line 2, this is now just rejected at compile time because it doesn't allow us to pass in the string to a parameter which is a num. The second program is allowed as before because Dart 2 has a concept of implicit downcasts. And so this is some place where we will still insert a runtime check in Dart 2, but now there is no checked mode, so you can't opt out of it, and the check is always there. And then the final example is the covariant generics example, where we have to check the argument to y.add. We have to verify that it's an int. And this is another situation that we have to preserve the type check in Dart 2, and we can't opt out of it. So the Dart 2 type system gives us soundness. Assuming that all the runtime checks that are required have been performed, then everywhere that there's not a check, we can actually know that the type is going to be true. There's a formal definition of type safety, which is very complicated to discuss. But at an intuitive level, what it means is if you write a type for some variable, then you can be sure when the program runs that the value in that variable will actually have that type. And now the compiler can optimize based on it. So the first thing we'll look at is how the compiler can use these new types in order to optimize the code better. And then we're going to look at how the runtime type checks provide a challenge. Because now in Dart 2, we actually have to run them all the time. We can't just turn them off. So then we're going to see how we applied other optimizations to get rid of the type checks. And on the whole, make the system faster. So to talk about why the types are important, we need to think about ahead-of-time compilation. So whereas in the Jit, we compile code on the fly as the program's running, and we can de-optimize it or recompile it whenever we want. In ahead of time, we need to compile all the code up front, and then save it, and then that's it. There's no more recompilation, no more optimization or de-optimization that can be done. The program is just compiled and it's finished. It's like similar to if you compile a C program or Objective-C. And this ahead-of-time mode is what you get when you compile your Flutter app in release build, for example. So the start of the ahead-of-time compiler, in order to make any kind of optimizations like we did in the Jit, we need some type information. So we start with the sound type system, but then we also enrich it with an analysis called type flow analysis. This allows us to get more precise types for a lot of variables in the program than we would normally have with the type system. In addition, it allows us to examine the code in a whole program way. Meaning, with the normal type system, you have a function, you define some types for the parameters, and then you analyze the function in the context of that. But in a whole program optimization, we can look at all of the call sites of some function, and then optimize the function more aggressively based on knowing exactly how it's called. For example, a function might be written that it takes a parameter which is a num, but we can see all the call sites actually just pass in ints. And then we can say, actually, the parameter type is just an int. So after we run type flow analysis, we then take the abstract syntax tree for the original program, and we add some annotations. So the annotations are highlighted here in blue and green. And these give us some of the information that we normally would have taken from the runtime profiles in the JIT. So in this case, the green one is telling us that some variable has a type which is more precise than the one that the type system says. And the blue ones are telling us that some method calls can be resolved to a specific function, rather than any set of functions that are inherited from some class. So then the rest of the pipeline is quite similar to JIT. We use the type information to generate the optimized SSA. The only difference now is that here we don't have any speculative instructions. So there's no check SMI or check class or anything that can fail. All the assumptions that we make are things which the type flow analysis has proven to be true. So there is no possibility that we'll have to generate new code or go back to unoptimized code at runtime. The code we generate now and the assembly code we generate is final and will work in all situations. The other aspect of the ahead-of-time compiler, which is not strictly necessary with the Dart 2 type system, but makes it a lot easier, is that it's a whole program. So whenever you compile a program for example, you compile your Flutter app in release mode, you cannot introduce any more code later on. And you cannot compile different packages of the program separately and link them together, like in C. Rather, the whole program is compiled at once. And that allows us to get a lot more precise type information than we could otherwise. So the most important way that we use the Dart 2 type system in the compiler now is the type flow analysis. So type flow analysis is a whole program analysis, and it infers more specific types than the type system gives us, but it can fall back on the type system whenever it gets confused. So there are many cases in the analysis where we have to do an approximation. For example, if you have recursion and the result type of a function depends on the parameter type, for instance, or the result type depends on a recursive invocation. How do you approximate that? Well, you can take the static type and just go with that instead. So even though type flow analysis gives us more precise types than the user writes, it is really important to have those types there as available in order to fall back on when the analysis gets confused. In addition, because it's a whole program, it's very precise but also very expensive. So this is why normally when you compile like a Flutter app in release mode, it takes a while. Most of that time that is compiling is spent in the type flow analysis. So we can see how that allows us to optimize our sum squares example from before. So we bring back the type annotations for list and output parameters, and then the stuff in italics is what the type system infers. So it now infers that the type for x is going to be an int, and it infers that sum is going to be an int. Then we plug it into type flow analysis. So type flow analysis generates something called a summary, which is kind of a simplified version of the program that manipulates only types and not values. It's the most similar thing we have to the unoptimized code in the ahead-of-time compiler. And the point of the summary is to collect this type information that we normally would have collected from unoptimized code. So here in green, we can see how we devirtualize the call to .forEach. So on the right, we call the underscore list constructor, which represents the fixed length list. And then that type goes into the call to sum squares, which then flows into the call to forEach. So after type flow analysis is done, we'll see that the call to forEach on the left is calling exactly forEach from underscore list, and not forEach from underscore growable list or any of the other subclasses of the list type. So once we create these summaries, we then use a work list algorithm. So we start off with an invocation. An invocation is a method name and a set of types. So we start off with just the method name is main, and the set of types is empty, representing that's where the program starts. And then we execute the summary, which produces new invocations. But unlike in a real program where you have to call a function separately every time with the different values, here we only care about the different types that it gets called with. So we can cache them. And once we process a function for some set of types, we can just reuse it again to know what the output type is. So this means that running type flow analysis is not the same as running the whole program, but rather it's a more abstract interpretation of the program. So in this case, we see how we devirtualize the arithmetic operations inside the closure. In this case, we had to make an approximation for the x parameter to the closure, where we couldn't infer a specific type. So we go with the type the user wrote, which is dart.core::int. Then we specialize it. This means that we take the type, which is int, and we look at all the possible subclasses of int in the program. In this case, there's only two, which are the internal types under smi and under mint. And then we know that the type for x is precisely the set of those classes. Finally, we look at the operations which are called on it. In this case, the operation is star. And we see what happens if you call star on underscore smi, what happens if you call star on underscore mint. Well, in either case, you end up calling integer implementation, ::star. And so this shows up finally in the annotated AST, where we can see that the arithmetic for plus and star have been devirtualized. So now when we compile this code, we don't need to make a method called a star or a method called a plus. And the same for each and add. We can just do regular arithmetic, and we can use the functions that we know specifically are going to implement for each and add. And so if we look at the optimized code, we can see that there are, again, no instance calls left in the body of the function. We have just the binary integer ops and some loads and stores as well, which is similar to what we saw when we optimized the code in the JIT setting. Only now we've used type flow analysis rather than the runtime type feedback. And then you can verify this assumption in the assembly by seeing that the binary int ops just translate into mul_q and add_q instructions. So this is the way that the Dart2 type system has positively affected the compiler. So now we have more information to use in the AOT compiler. We can generate faster and smaller code. But as I said before, we have all these runtime type checks now, which we have to stick in the code. And those obviously can make the code slower. So how do we address that? Well, we have a number of solutions. So there are many different types of calls. Unlike in Dart1, not every type can be wrong, but the typecasts are inserted at specific points that we can identify in the compiler. And we can address each of these types separately. So for some of them, we apply optimizations to make the type checks really fast. And for others, we have optimizations that allow us to skip them entirely in situations that we know they're not needed. So the most basic case is an implicit downcast. So this code is allowed in Dart2, where we cast the list of num into a list of int, but the type system, which generates this AST on the right, inserts a typecast explicitly. The second type is for a dynamic call. So in Dart2, you can take any variable and cast it to a type called dynamic, and then with dynamic, you can call any method you want with any number or type of parameters. This means that whatever function eventually receives this call has to then check those types and check the number and type of parameters. And since any non-static function could be called dynamically, then we have to add these checks to all of those. We also have to add them to closures as well, because Dart2 has a type called function, which is not exactly like dynamic, but is quite similar in the sense that you can call it with anything you want. And then finally, we have the covariant generics problem as from before, where you try to add a type that, in this case, it succeeds, but we would still normally have to add a check to the add method that we weren't passing in something like an int. So the first way that we address this problem is by making type checks fast. So when we compile a program in AOT, we create a pre-ordered traversal of all the classes in the program according to the inheritance hierarchy. This means that if we want to check what classes are subclasses of a specific class, we can just check the range that starts from the leftmost to the rightmost child. So if you do a cast like x as num, then it just is a range check. So in this case, we're checking the class IDs from 48 to 50 with the addl and compl instructions. So this is a very fast kind of check. If you have generics involved, then the check is a little bit more complicated, and we use a cache. So in this case, we create a table which has all of the types that we've seen and the type we're comparing against, and then we just check whether the type is any of the ones that we've seen and tested already, and then we know that it'll succeed. And if it's not found in the cache, then we go into the runtime, which is C++ code, and then that is a much slower way to check the type. So finally, one way that we made the type checks faster in Dart2 specifically is with type testing stubs. So for many types, we generate a function which is personalized for that type. And that function's role is to just take in a value and check it against that type. So in this case, and this is specifically useful for generics. So in this case, we have to check the value parameter to a growable list. So what we do here is we generate a type testing stub for every value that t might be. In this case, it's num. And then when we need to do the check, we take the object which represents the type, which we have because we have reified generics, and then we just call the function which is stored on that type in order to perform the check. And so this way we can get back to using a range check for x as t, even though just from the x as t itself, we don't know what type it's comparing against. So this is how we made the checks faster, but we also did a lot of work to remove them entirely. So with dynamic invocations, for example, so in this case, we create a list, and we put it into a dynamic variable called x, and then we call skip. So normally skip gives you an iterator that skips the first n elements. But in this case, we pass in a string instead of an int, which is OK because it's being marked as dynamic. But we can identify all the dynamic call sites, and we rewire them to have special names. So on the left, you can see instead of calling .skip, we call dyne:_skip. And then on the right, we generate a function which performs all the checks, the assert assignable instruction in this case, and then delegates to the regular skip method, which doesn't have any of those checks. So this means that for normal methods which don't involve generics, for instance, we don't have to perform any checks at all, even though it could somewhere be called dynamically. The second thing we do is multiple entry points to deal with the covariant generics case. So in this case, we have a check for the parameter of add, as before. But we can't eliminate this in all cases. However, we can identify that certain calls to add are going to be safe. So in this call, we know it's going to be safe because we never upcasted the type of x. So when we call add in this case, we say we're using a different entry point. And that means that whenever we jump to the function, we jump into a different point in the assembly. So here we have, in yellow, we have the two entry points. The first one is the checked one, and it calls the type check. But then the second one is at the bottom, and that skips all the checks. So how do we detect which call sites can use this? Well, this comes back to the way that we gather type information in the different modes. So in the ahead of time, we represent these type checks explicitly in the type flow analysis. And we can detect if they never trigger in type flow analysis, we can be sure that they're never going to trigger at runtime. And we can either delete them entirely or skip them at the call site. And in the Jit compiler, we use the inline caches, which are the way that we perform, that way that we collect the profiling information for the receiver of a call. So whenever we're checking which receiver is this method call against, we also check the type arguments. And if the type arguments match the call site exactly, then we know we can skip any checks on the target. So those are the ways that the optimizations that we do to remove the overhead of type checks. At the beginning, the Dart 2 performance was not very good because of type checks. But now these, in most programs, these type checks are not visible at all in the profile. So I think we've done a very good job of eliminating these. So that's what Dart 2 has been like for the compiler as a whole. There are a lot of opportunities to do new optimizations that we couldn't before, and then the challenges of getting rid of these type checks. Overall, we've improved the performance for the AOT compiler, which is very relevant to Flutter apps. But we've only started to scratch the surface of what we can do. Soon we're going to have non-nullable types in Dart, and that's going to give us a lot of new opportunities for using the type system. For example, we can unbox integers more aggressively. Normally, when you write an int in your code, it can be any 64-bit int or null. But there's no way to represent 2 to the 64 plus 1 possible values in a 64-bit int. So we have to box it, and we make an object which carries around the number or can be null. This is, of course, slower than representing the number inline. So when we have non-nullable ints, there will be a lot of places that we can just represent an int as an int directly and not have any container objects. It will also allow us to have more opportunities with modular compilation, which would be where you could compile multiple pieces of an app separately and link them together. Or you could deploy an app and then add code later to it with a code push kind of mechanism. This is not possible today because the type flow analysis is whole program, and we assume that we know all the code that's going to run upfront. But if we didn't have type flow analysis, then we could use the types more aggressively and compile the code in a modular way. So yeah, that's everything I have to say. Thanks for listening.
Thanks for the presentation. I have one question. You said about modular compilation. Does it mean that these modules can be compiled in parallel? Like for example, in Flutter or something like that, when you compile Dart code in AOT?
So modular compilation is in the future work section, so it's not something we've done now.
Yeah, but if it's done.
Yes, in principle, yes.
Okay.
It would allow that. But modular compilation is not the way to make the AOT compiler faster. I mean, it's maybe one way, but there are many ways that we could parallelize it today without doing modular compilation.
Okay, thanks.
Any other questions? Thank you, Samir, for the presentation. I have 3 questions. First of all, having the better type inference system, does it also enable better, static code analysis on the tooling level?
So yes. So there's two kinds of type inference. The one kind happens sort of at the language level. It's specified how type inference for Dart should work. And it infers types, and these inferred types can actually change the behavior of the program. For example, if you write var x equals 0, x equals 1.0, this code will not compile because it will infer the type of int for x, and then it will not allow you to assign 1.0 later on. This is the first kind of type inference. This is the kind of type inference that is already available or already used in the IDEs and the editors. The second kind is the type flow analysis. So this type flow analysis produces much more precise results. However, it takes a long time to run. So it could be useful for some kinds of static analysis if you want to look for certain kinds of bugs, but it would not be responsive in an IDE if you wanted to use it for completion or anything.
Okay, so for now it's too slow. Probably when we are, better CPUs, it might be that useful.
When we have better CPUs, we'll make it do more work and be smarter. But it is potentially useful if you want to have other kinds of analyses that you want to run on the whole program to catch bugs or something.
So my second question is type inference. So if you do int x equals whatever, or var x equals something, is the int thing faster to be compiled or not? Or doesn't make any difference?
Within the VM, so the VM is the back end of the compiler. There's 2 parts of the compiler. The front end generates an AST where all the type checking and type inference is complete. Then the VM compiles the AST in a machine code. The VM doesn't care. It's going to look the same either way. Within the front end, someone who works on the front end would be better qualified to answer. But I would guess that it's not much of a difference.
So the last question, in Java or whatever, we always were taught to have if we can have a final value, mark it final blah. And in Dart, all people claim to say that you need to not final but var. Why? I know it's a language question more, but design question.
Personally, I use final whenever possible, so I wouldn't answer that.
Thank you very much. Thank you, Samir. Big round of applause.